Hello everyone, welcome to another episode of Beacon Wins Science. Today in this video, we are going to discuss a very important category of organic chemistry reactions. This category of reaction is known as the addition of nucleophile to carbonyl group. The Grignard reaction also belongs to this type of category. This is very important category and you have to understand what are carbonyls, what are the nucleophiles, how we can improve the reactivity of the reactions, how the addition of acid and base can improve the reactivity of these type of reaction. Also in the end we will discuss about everything about the Grignard reaction, all in this video. So stay connected till the end. First thing first, what are carbonyl groups and how are we going to identify them? The answer is the C double bond O group. Any form of aldehyde, ketone, carboxylic acid, acid halides and many other compounds came under the carbonyl group. For example, these molecules are having C double bond O group in it and this group is known as carbonyl group. Now, after understanding what are carbonyls, we have to understand now why nucleophile chooses to attack to the carbonyl group. For this, we have to see closely the structure of the carbonyl. Let's observe the orbital structure of carbonyl group closely. In carbonyl group, the carbon atom is attached with oxygen atom via double bond, like that found in alkenes. In this double bond, one bond is a sigma bond and the other is the pi bond. This sigma bond is formed by the head-on overlapping between sp2 orbital of carbon and oxygen, while the pi bond is formed due to the lateral overlapping between the p orbitals of carbon and oxygen. As we have discussed the sp2 hybridization in carbonyl compound, the group will remain planar at the angle of 120 degree. You can see the structure here closely. Now, as we know, oxygen is more electronegative compared to carbon. The pi bond in the carbonyl group get polarized due to the electronegativity difference. This polarization is the key factor for the reactivity of the carbonyl group. Now, as we know, due to the high electronegativity of oxygen atom, it attracts the pi electron cloud more towards itself, creating a partial electron deficiency or partial positive charge over the carbon atom of the carbonyl group. This charge attracts negatively charged or electron-rich nucleophile towards itself. Now, when the nucleophile attacks the carbon atom of the carbonyl group, the pi bond starts broken and the new sigma bond starts building between the nucleophile and the carbon atom. The pi bond electron shifts to the oxygen atom completely, making it negatively charged O-. You can see all this happening here in this diagram. To explain the nucleophilic attack over carbonyl species, we have chosen cyanide Cn- group as a nucleophile. The Cn- attacks to the carbon atom of the carbonyl group and forms a bond which is a carbon and a Cn bond, and breaking the C double bond O group into a CO group and having a O- charge over the oxygen. Take for instance both ketone and aldehyde. As we can see in both, the mechanism of action is same after Cn attack. The pi bond between the CO group shifts towards oxygen atom, making it negatively charged, which was stabilized by the H plus donated by the acid. After the attack, the intermediate is formed, which is known as cyanohydrin. The cyanohydrin are very useful intermediate in many natural and industrial products. But the cyanohydrin is not much stable and it is reversible, which means it can again go back to the carbonyl group, leaving Cn group as Cn- as it is a good leaving group. This cyanohydrin formation is more favorable for aldehyde as compared to ketone, because in this reaction carbon atom of carbonyl group is shifting from sp2 hybridization to sp3 hybridization, that is from double bond to single bond, which causes a decrease in the bond angle between the two atoms attached with the carbon atom. The bond angle in sp2 hybridization is 120, degree, while in sp3 it's roughly 109 degree. In aldehyde, the H atom, which is small in size, does not create much steric hindrance to the upcoming CN group, resulting in a stable intermediate, while the ketone carries a large alkyl group can create a good amount of steric hindrance to the upcoming CN group. That is why aldehyde makes a good stable cyanohydrin intermediates.
So far, we have discussed so many things about the carbonyl chemistry. We have seen how nucleophile attacks to the carbonyl group. Now, it's time to understand how hydride group attacks to the carbonyl group. This is very important because this is the major reaction which is used for conversion of carbonyl groups into the alcohol.
Now, the reduction of carbonyl also follows the same mechanism as we have discussed in this video so far. Here in place of CN group, the hydride group H- attacks to the C double bond O group, resulting into the addition of H group to the carbonyl carbon, and O- atom which get stabilized into OH by gaining the H plus species from the reaction mixture. Now the source of nucleophilic hydrogen atom can be sodium borohydride NaBH4 or lithium borohydride or even sodium cyanoborohydride and many more other. Let's see how this reaction works. We can see here when we carry out this reaction with carbonyl carbon, then the hydrogen atom attacks with the pair of electron from the BH bond will be transferred to the carbon atom of the carbonyl group. This is what known as hydride transfer. Here in this case, the scenario is same, just like what we have seen in cyanohydrin reaction case. The aldehyde reacts faster than the ketone for the same steric hindrance reason.
Moving on to the next portion for the carbonyl group reaction, and we have chosen the very important and interesting name reaction, the Grignard reaction. In this reaction, the reagent which we use is organometallic reagent. Let's understand this reaction more closely.
This is pretty simple. Suppose you have an organometallic reagent like phenyl magnesium bromide. In this reagent, magnesium, which is very electropositive metal, directly connected to the carbon atom. So in this case, the polarity is more shifted towards carbon atom, generating a charges among carbon negative charge and magnesium having a positive charge. So the carbon here will act as a nucleophile and attack to the carbon atom of the carbonyl group, resulting into the formation of new CC bond and the breakage of the pi bond between C double bond O to give it alcohol as a product. One thing very important about this reaction that we must keep in mind that this reaction organometallic reagents are pyrophoric and can catch fire very easily, so keep them away from water. For this reagent, trace amount of water can also be very dangerous. Also, this reaction is generally performed in low temperature as low as minus 78 degrees Celsius, which can be maintained in lab by adding acetone to the dry ice in a tub and keeping the reaction in that tub. Because they are so reactive, so the solvent used in these type of reaction is aprotic, which does not have acidic proton like THF, diethyl ether or toluene, because protic solvent can react with Grignard reagent creating a stable alkane. Few more things you have to keep in mind while putting this reaction. This reaction should always be carried out in dry condition in inert atmosphere of nitrogen or argon because organometallic reagents are readily reactive with oxygen. And the last but most important thing about this reaction is that after the completion of the reaction mixture must be quenched with ammonium chloride. Additional information. These Grignard reagents were discovered by Victor Grignard in 1871. At the University of Lyon, he got the Nobel Prize in 1912 for his discovery.
Let's think, if we add water to aldehyde or ketone, what will happen? The answer is formation of the diol. How it will form and what are the restriction and limitation about this reaction, let's understand this.
First, this reaction is generally backward favor reaction, which means After diol formation, it will reverse back to aldehyde or ketone, which is more stable. Second, the possibility of diol formation in aldehyde is more as compared to ketone for the same steric hindrance reason. The best known example to explain this reaction is formaldehyde in water. Since there are not much bulky groups in formaldehyde, the diol formation is possible. The aqueous solution of formaldehyde contains no C double bond O group. It's a diol group that is present in the aqueous solution of formaldehyde. Let's understand what are the other factors that can increase the chances of formation of diol with water in carbonyls. The other factors is the presence of the electron withdrawing group next to the carbonyl group. The electron withdrawing group further reduces the electron density on the carbon atom of the carbonyl group, which further favors the attack of water molecule to the carbonyl group. For example, trichloroacetaldehyde, which can be completely hydrated in water. Now, if I ask you whether hydration is possible for cyclopropanone, the answer is yes. But the explanation here is little different. The bond angle of sp2 hybridized carbon atom is 120 degree, and in cyclopropanone, the carbon of the carbonyl group has a bond angle of only 60 degree because it is restricted in a triangular structure, which means 120 minus 60, it is having a 60 degree distortion. Now, if water molecule attacks this carbonyl carbon, the hybridization will be changed to sp3, and the bond angle for sp3 is 109 degree. Now 109 minus 60 is 49 degree distortion, which is less compared to the 60 degree distortion and provide it more stability from strain. That's why it is favorable.
Just like water, alcohols can also attack to the carbon groups because it is also having a nucleophilic species O, oxygen atom, and it reacts with the carbonyl group to form a hemiacetal.
One interesting example, you can see it here, where intramolecular reaction happening, resulting into the formation of cyclic hemiacetal product. But this cyclic hemiacetal formation is common only if it is forming 6 or 5 membered ring, and not for other rings because of angle strain in other cyclic rings. Nucleophilic addition reaction to the carbonyl group can be catalyzed by adding acid or base to the reaction mixture. If we add acid to the reaction mixture, the oxygen of the carbonyl group attracts the H plus ion, resulting in a positive charge on the oxygen atom, which makes it more powerful electron pulling, resulting into the shift of double bond and making carbon electron deficient. Now, if we use base, the base will attack to the nucleophilic group, resulting into the extraction of the proton from the nucleophile, making it more negatively charged nucleophile.
In this video, we have tried to touch so many different parts of addition of nucleophile to the carbonyl chemistry, and I think we have discussed many portions. Now there are so many other things remain in this topic. We will try to cover it in the part 2 of this video. Also, if you find this video interesting and informative, please comment down us what are the things you love the most and if you have any question regarding this topic. Also, give us a big thumbs up because we need your support. If you want to watch such kind of organic chemistry informative videos in this channel, subscribe to our channel. See you in the next video.